So this is Analog Circuit CC201 lecture 2. Yesterday we started off by looking at a very simple nonlinear network, one using only one nonlinear element, that nonlinear element being the diode. The network itself, we call this V1, a resistor R1 and a diode D1. The voltage across the diode was denoted by capital V sub D, and the current in the loop was denoted by I. Okay. And from the theory of semiconductor devices, it follows, okay, that Vd can be written Vt ln I by Is. Okay. And this is assuming the diode is operating in the forward bias region. And at this point and in this course, we will not be too concerned about how this logarithm came about, or how the physical construction of the diode influences this nonlinear function or Is or anything else for that matter. We just take this as a given. Okay. Now, given that Vd is of this nature, we can write Kirchhoff's current law in the loop and conclude that V1 is IR1 plus Vd, which happens to be Vt ln I over Is. Okay, this is what we did. Yes. This is clearly a nonlinear equation in I. And to find I, what would we have to do? You solve it. I mean, this is a nonlinear equation. If you can approximate it, well and good. Otherwise, you take it to a computer. Is is known. Okay. Is R1, V1, Vt are known. So, which means you can solve for I either numerically or approximately. And this is what we saw yesterday. We saw one very simple approximation. We just exploited the fact that the exponential is a very sharply rising curve. So to a 0th approximation, you can approximate the voltage drop across the diode when it's forward biased to a constant volt. Okay, that constant value being about 0.65 volts. All right, and that voltage is called the cut-in voltage of the diode. Right. In any case, even if you don't make the approximation, you can go to a computer, use MATLAB, whatever, to go and find I. Okay. Now, the key point here is that even when there is a single nonlinear element, life is sufficient. It has become much more complicated than what we were used to, right? If instead of the diode you had a resistor, you would simply get V1 to be equal to IR1 plus I times R2. You have an algebraic simple linear equation. You go and plop, move things around and find I. Okay. Things have now become fairly complicated. So you can imagine what will happen when you have more and more nonlinear elements, okay, in a network. I mean, you would expect that when you had a linear network, what would you get? You would get a system of linear equations. So now when you have many nonlinear elements, what would you get? What can you expect? To find the loop currents when you had a linear network, you would have a bunch of linear equations, correct? So now when you have nonlinear elements, based on this very simple example, what can you expect? You'll have a bunch of nonlinear equations in the branch currents, okay? Alright, and hopefully a computer will be able to solve them, okay? So now, let's say we've solved this nonlinear equation for I, okay? Now, let me pose a slightly different problem. Now, if instead of applying V1, I applied V1 plus delta V, okay, where delta V is very small, what would you expect the current? I mean, going forward, we will define what this very small means. Please note that nothing in the world is really small or really large. Small and large are in relative terms. So we have to define, when we say something is very small, we have to define what this very small is, and we'll be doing that as we go along. Okay, but for this moment, let's assume that this delta V is very, very small. So what can you expect? I mean, do we have to go and resolve the nonlinear equation again, or do you think it's possible to? What would you expect about the current? If the applied voltage V1 changes by a small amount, what can you expect the loop current to be? Will it be the same? No. Okay. Will it change? Obviously. Okay. So one thing we can reasonably expect is that if the change in V1 is small, then the change in I1 is also probably small. Okay. So let's denote the new current by I plus delta I. So Kirchhoff's law has to be valid even for this loop. So V1 plus delta V must be equal to I plus delta I times R1 plus what? Vt ln of I plus delta I by. From the earlier network, what can you say? V1 was equal to I times R1 plus Vt ln I by Is. Okay, this is what we had earlier. When I say, okay, this is what we had earlier. Okay, and this is what we have now. All right, and all right. Now if I said delta V is very small, okay, and let's say we've already put in all the effort and solved the lower equation numerically. The question is, given that the change in the applied potential is so small, the question is, should I go through this entire numerical solution procedure again, or is there something smart I can do and find the new current? Does it make sense? See, let's say I've already put in a lot of effort, okay, and found I in this network. The question is, if I just changed V1 by a very small amount, delta V, should I go through the entire procedure again, or is there a smarter way of figuring out what the new current will be? Okay, so what can we do? Any suggestions, comments? Pardon? You can subtract the two. Okay, we know approximately what I is going to be. We were only interested in finding the change in the current due to a change in the applied voltage. You understand? If I find delta I am done, because the total current is simply I plus delta I. I has already been computed. So the only thing I need to find is delta I. Okay? So if I subtract these two equations, so if I call this equation 1 and call this equation 2, 1 minus 2 will give me delta V is delta I times R1 plus Vt ln of I plus delta I by Is minus ln of I by Does it make sense? Okay. So is there any approximation in this in the story so far? There is no approximation here at all. Okay. So far everything is legal. Now, if delta V was very small, then you can say delta I is very, very small. Okay. Then what can we do? Okay. What we can do is, please note that this is some function f of I plus delta I. Okay. This f of x happens to be ln x. That's all. Okay. So you can write f of I plus delta I as, you know the value of a function at a point. You want to find the value of the function at a point very close to this point. So who is going to help you? This, to a fairly good approximation, this is nothing but f of I plus df by di. Actually it should be the argument, right? So let me call this argument x. So df by dx evaluated at x equals I multiplied by delta. Okay. What series is this? This is the Taylor series, where all the other higher order terms have all been truncated, right? We assume that they're so small compared to this first order term that we can neglect all of them, and that is only valid when this delta I is very, very small. Okay. So now getting back to the particular functional form, what happens? Ln of I plus delta I by Is can be written as approximately, if delta I is very, very small, this can be written as ln of I by Is, okay, plus delta I by, is this right? Does it make sense? This is nothing but the derivative of the logarithm evaluated at I. Okay. So in other words, this is given by approximately ln of I by Is plus delta I by delta V is nothing but delta I times R1 plus Vt by I times, alright. So what is the great thing that we have accomplished now? So what? If delta V is delta I times R1 plus Vt by I times delta I, how do we proceed now? Pardon? So we already know I. Okay. So, and I happens to be the current in the loop when a voltage V1 was applied. Okay. We are interested in finding the current in the loop when the voltage applied was changed from V1 to V1 plus delta V, where this delta V was a small increment around V1. And this increment in V1 causes an increment in the loop current. Okay. And by writing the Taylor series for the nonlinear element, we see that if this increment is sufficiently small, where we will define sufficiently small a little carefully later on, for the time being, it is seen that if this increment is sufficiently small, then the increment in the applied voltage can be related to the increment in the loop current by what kind of equation? This is a linear equation. You understand? So, which means that if you knew capital I in the first place, okay, then you could compute delta I from delta V divided by R1 plus Vt by. Do you understand? So what are the two assumptions made here? So delta V is the so-called small terms. Okay, so as far as this discussion is concerned, what I wish to point out is the following. If you have a nonlinear network, okay, you can relate the change in the current and voltage. Okay, for example, in this case, you can think of the stimulus as this V plus, as this delta V signal being added in series with V1. Okay, and the response as the loop current. Okay, it was I earlier, it is now I plus delta I. So even though the network is nonlinear, one can always relate the change in the current in the loop to a change in the applied voltage through a linear equation. Okay, and please note that this is not coming out because of some magical way in which I have chosen a nonlinear device. Instead of having logarithm, if I had any old function, okay, any nonlinear function, this whole approach still works as long as the applied change is small. Okay, in more textbook terms, if the applied stimulus is changed by a small amount, or in other words, the signal applied is small, okay, the loop currents in a nonlinear network, okay, and node voltages will also change by a small amount, and while the absolute voltages and absolute currents are still related by a nonlinear equation. Please note that equation 1 here relates the absolute voltage to the absolute current. What is the absolute voltage? What is the absolute voltage? V1 plus delta V. And what is the absolute current? I1 plus delta I. Please note that the absolute voltage and the absolute current are still related by a nonlinear equation. However, the change in the voltages and current, okay, that is delta V and delta I, are related still by what? By a linear equation. Okay. Alright, so in other words, so what kind of network implements this equation? Can you think of a linear, if this is a linear equation, it must be coming from a linear network, right? So what kind of network do you think will have this loop equation? Pardon? What kind of network? Okay, what resistance? Can you be a little more specific? This is the loop equation of a network. Can you tell me what the network is? Very good. It's a network with a voltage source of value what? Delta V. Okay. And what? R1. Okay. And a resistance. What is Vt? What is Vt? Vt is the thermal voltage of Kt by Q, which is about 25 millivolts at room temperature. So in other words, you can, and if this is the network, then delta I is the current in this. So in other words, as far as incremental signals are concerned, okay, however nonlinear the network is, one can always draw a linear network which relates all the incremental quantities. Okay, so please note that this is the incremental network. Okay, so all the fixed, the original voltages are all gone now. Okay, that V1 is not there anymore, the I is not there anymore. What you have are only the incremental quantities, which are delta V and delta I. Okay, you understand? So given delta V, you can find delta I, and to find the total current, what would you do? What would you do? The total current will simply be I plus delta. Okay. So this can be extended to an arbitrary nonlinear network. Okay. So if you have any network branch, okay, where you have I and you have V, which is some function of I, for example. Okay. So you had the original network with many such elements for argument's sake, and as we did with the diode example, we find the value of we find all the branch currents and node voltages by beating our heads against the wall, right? Because all these are nonlinear equations, you had to either go to a computer or do something really clever to figure out what these the quiescent currents and quiescent voltages will be. So okay, so that's what we did when we solved. That's what we did when we solved this equation numerically, correct? So for an applied V1, we'll be able to find I. Now this can be extended to any arbitrary network. So let's consider one particular branch of that network where some current I was flowing, and the voltage across that branch happens to be some nonlinear function of I. In the case where it's a diode, this particular nonlinear function happens to be what? Of this logarithmic form Vt ln I by some. In practice, in general, it could be anything. Okay. Now, let us say we introduce a small signal voltage source somewhere inside the network. So, in other words, some voltage which was V1 earlier has now become V1 plus delta V. Then what can you say about the current through this particular branch? Do you understand the question? Okay. So, let's say we had some kind of arbitrary network. Okay. This was V1. Okay. And we had this nonlinear block, okay, and we numerically found I. Okay. Now what I do is the following, which is I take the same network, okay, and instead of applying V1, I apply V1 plus delta V1. Can you make any comment about what will happen to I? Hopefully, if delta V1 is very small, I will also change from what it was to something else. Hopefully, the change is small, so the current will become I plus delta. Okay? Alright. So, V, and let's say the original voltage across this network, across this element was V. Now this voltage is going to be, any comment on what the voltage across this branch is going to be now? The current through the branch is changed by a small amount. So what do you think will happen to the voltage? It will also change by a small amount. So which let's call that V plus delta V. You understand? Okay. So how do we now relate delta I to delta V? V was f of I. Okay. What else? V plus delta V is f of why is this true? Because the governing relation between the I and V of the device is some functional form A. Okay. If a current I was flowing, okay, as in the diagram here, okay, this is the same network N. If a current I was flowing in this first network, then V is f of I. In the second network, the current flowing is I plus delta I, and the voltage across it is V plus delta V. So V plus delta V must be equal to f of I plus delta. Okay. So now from these two equations, what do you get? What do you see from this? So from you write the Taylor approximation for the second equation, V plus delta V is approximately equal to f of I plus f dash of I times, okay, and V happens to be equal to f of I. In other words, delta V happens to be f dash I times okay. So what is the bottom line? While it is true that the element is nonlinear and could be horribly so, if you change the voltage across this nonlinear element by a small amount, you can always relate the change in current through this element by a linear equation. Okay? And what are the dimensions of delta V by delta I? Okay? What are you used to typically if you say given a resistor, what is the notion of resistance? How will you measure a resistor in a lab? You will apply V, you find I and do V by I, and that's R. Okay? That's only valid because the resistor is a linear element. Okay? Now, when you have a nonlinear element, you can still have a notion of resistance. However, the resistance is not defined from not just V by I, it is delta V by delta I. Okay? And what does it depend on? The delta V by delta I depends on I. Okay? So this value, the original value capital I of the current flowing through the nonlinear element in the first place is called the quiescent current. Okay? Alright? Or often called the quiescent operating point of the nonlinear device. Okay? Does that make sense? Alright? I is the quiescent current. Alright? Delta I is we will be repeatedly using these terms. Delta I is called the incremental current. Okay? V is called the quiescent voltage, and delta V is by the same token called the incremental voltage. Alright. So while it is true that the quiescent voltage and the quiescent current are related by some kind of nonlinear equation depending on the physics of the device inside, incremental current can be related to the incremental voltage by a linear equation. Okay. To show you a diagram, let me take again the case of a diode. As I said, I versus V. Okay, the exponential, so it does something like this. Okay, so this is Vd. Okay, this is Id. All right. So let us say the voltage is V, the current is. Okay. If you had a linear resistor, what kind of curve would you get here? You will get a straight line. Okay. So clearly, because non-linear, you get some weird shape. Okay. And clearly, you see that when I reduce the applied voltage by a factor of 2, the current reduces by more than a factor of 2. Clearly, indicating non-linear. All right. However, if I change the applied voltage by a small amount delta V, okay, so let me say this voltage is V plus delta V. What do you see? The current has also changed, and if I make this delta V tend to 0, then the change in the current will also tend to 0. So this, the point here is I plus delta I. Okay, so that is this point here. So clearly from this triangle there, okay, so I'm going to enlarge this triangle. Okay, what is the base of this triangle? Delta V. What is this? This is delta I, and if delta V is sufficiently small, okay, this can be, I mean, in reality, is this a straight line? In reality, this is not a straight line. Okay, this guy here. This chap here is not a straight line. Okay. However, for sufficiently small delta V, okay, it can always be approximated as a straight line, and the slope of this triangle is the slope of this curve at this point is simply nothing but df by, what is the slope of what is the slope of this hypotenuse here? It's nothing but del I by del V. Okay, and that is nothing but dou df by, is nothing but did by dvd evaluated at vd equals, okay. In other words, the ratio of the incremental current to incremental voltage, okay, can be is simply a constant, provided the incremental voltage is very, very small. So just like how I by V is called the conductance, delta I by delta V is called the what? Conductance relates current to current and voltage. Okay. We now are interested in relating incremental current with incremental voltage. So what would you call it? It's called the incremental conductance. Similarly, delta V by delta I is called the incremental resistance. Okay, and both, so the incremental conductance or resistance depend on what? Very good. So clearly the slope of this triangle of this curve at this point depends on where you are along the curve, right? So, and where you are along the curve is given by this abscissa ordinate pair V comma I, correct? And this set of points, okay, depend on V I. All right. So this, so what is V? We said V is the quiescent voltage, I is the quiescent current. Okay, so this combined pair V comma I, okay, is often called the operating point of the nonlinear . So the bottom line is that while the absolute voltage and the absolute current of a nonlinear device can be related in any arbitrary nonlinear fashion, it still follows that incremental changes in voltage across the device will result in incremental changes in the current, and the incremental change in current can be related to the incremental change in voltage through a linear equation. Okay. So for example, delta V by delta I has to be something of the dimension of resistance. However, this is not the same as V by I. Okay, it is delta V by delta I is the slope of the nonlinear characteristic at the operating point given by V comma I. So in general, when you have a nonlinear device, the incremental resistance or the incremental conductance of the nonlinear device, okay, is a function of the operating point. So if you're interested in finding, so turning the same argument upside down, if you're interested in finding the incremental resistance of a nonlinear resistor, what would you first need to do? You need to first find the operating point. Once you find the operating point, I mean, you already know the functional form, I is equal to f of v or v is equal to g of I, something like that. Once you find the capital I, to find, all you're interested in is finding the slope at that point. So you differentiate g of I with respect to I and put in the quiescent, evaluate that at the quiescent value. That gives you the incremental resistance, okay, or the incremental conductance of the nonlinear resistor at that particular operating point. Okay, so as long as you're always operating in a region close to this operating point, you can expect that if you change the voltage by 1 millivolt, for example, then you can expect the change in current to be 1 millivolt times the incremental conductance evaluated at that point. So to give you a quick example, for a diode, what is V? V is nothing but Vt ln I by Is. Okay. So I'm interested in finding the change in the diode voltage due to a change in the diode current. Okay, and what is that? Delta V by delta I is nothing but sorry, this is VD, ID is nothing but dou VD by evaluated at ID is equal to some quiescent current. And what is this? This is VT by I. So clearly the incremental resistance of the diode depends on operating point. What is operating point here? Is given by the quiescent current flowing through the diode, which is I. Okay, VT is the thermal voltage. So if you have 1 milliampere of current flowing through a diode, okay, what is the incremental resistance? You understand what's going on the last bench there? So if I is 1 milliampere, then delta V by delta I is 25 ohms at room temperature. Okay, so in other words, let's say if I had 1 milliampere in the diode and the voltage across the diode was say 672 millivolts. Okay, if I change the current to 1.1 milliampere, can you guess what the voltage across the diode will be? How will I find it? So the quiescent current through the diode is 1 milliampere. So what is the dynamic resistance of the diode or the incremental resistance of the diode? 25 ohms. Okay, so that what does this mean? It means that if there is a small change in the current through the diode, there will be a small change in the voltage across the diode, and the ratio of this change in voltage to the change in current is is 25 ohms. Okay, so what is the change in current? 0.1 milliamperes. So the total voltage across the diode is the quiescent value, which is 672 millivolts, plus the incremental value, and the incremental value is, it is the dynamic resistance 25 ohms or the incremental resistance times the change in current, which is 0.1 milliamperes, which is 2.5 millivolts. So when you have 1.1 milliamperes being pumped through the diode, the voltage will change and it will become 674.5 millivolts. Does it make sense? Okay, so good. So we'll continue to